I've worked on a couple of conferences in the immediate past, and one of the interesting things that happens is not a lot of people are familiar with building wireless networks that support extremely large numbers of users in very small spaces. The subject of high-density wireless networks seems to be a lot more relevant and interesting these days, given the amount of interest and capital that seems to be going into building wireless ISPs and hotspot deployments. And if this technology becomes truly ubiquitous the way cell phones are, then you all of a sudden have a problem supporting several hundred to several thousand radios in an extremely small space. Interestingly enough, IETF and NANOG are actually extremely good test beds for doing that. It's not that often that you can go someplace and find 500 to 2,000 active wireless users in one room. How do you keep them happy when you have them? Institutional knowledge on the subject of building networks that actually support this is extremely limited. When we started talking to vendors about products that might be able to do this, you get two sorts of responses. Some vendors don't even know how to test their equipment in an environment like this. And some of them say things like, well, cool, tell us how it goes when you're done. And that's not really a whole lot of support, especially when you're talking about buying $100,000 worth of equipment or something like that. One of the things that we can observe from having worked on previous events before the two that we started planning for last fall was various enterprise access point products get into serious trouble when they have more than 200 users. And that's a combination of properties. One of them is some of the cards that vendors manufacture only support 255 max on one side. So clearly if you get to that number, the whole access point blows up. Some of them simply, performance begins to degrade around 70 to 100 users, and by the time you get to 200, the access point is just in a state that it's not going to work. Radio interference, which is caused by other radios transmitting on the same frequency, either access points or clients, causes dropped Ethernet frames, and because the access points are designed to ameliorate that by caching the Ethernet frames and resending them, it results in queuing on access points. Since they only have 16 megs of RAM, you can only queue for so long. The most obvious impact of this is you start seeing greater than 1 second ping times or round-trip times for your packets to places that are immediately on the other side of the wireless network. When one access point gets into trouble, other access points tend to get into trouble because the clients that are on that access point roam over to another one, either because it's finally given up and crashed, or because the users move so that they can get better connectivity. The largest source of radio interference in any deployment seems to be the access points themselves and not the users when you have them close together, because the users are actually sucking down more traffic than they're sourcing unless they're running file sharing applications or something from their wireless network. If they're mostly web browsing or pulling down their email or watching streaming media, it's the access points that spend most of the time transmitting, and so it's the access points that end up stomping on each other. Site surveys and testing can't entirely eliminate any problems that you have. You don't know things like where all the users are going to sit when the meetings are out. You don't know what the performance characteristics of a room are going to be when it has an extra 200 tons of meat and water in it versus not having that. What do people want when they sit down and use a wireless network? Well, I mean, the basic thing is they want to get their work done. But they want to be able to roam between access points because when you move around, you don't want your connections to drop. You don't want to get a new IP address. You basically want to be on the same subnet. There are vendors who are moving into this space who do things like tunnel between access points on different networks. Some of them do extremely strange things. A lot of them look like gnats. I think probably the ultimate solution to the roaming problem is probably the ultimate solution to all roaming problems, which is some kind of IP mobility stack. We're probably still a long way from there. They want low latency and loss, which is to say that when they do something, they want it to work just like an Ethernet network or any network with desirable characteristics. They want it to work just like it does at home, because most people who go out and buy wireless equipment and deploy it at their house just plug it in and it works. And they have a reasonable expectation that they should be able to do the same thing here. So a couple of givens about that you can just assume when you're building one of these networks. In the U.S., you have 11 available channels. 3 of them are non-overlapping. The total amount of spectrum you have is 83 megahertz, and each of these channels is 20 megahertz wide. So, you know, that's how many you can stuff in there. Wireless cards with 30 milliwatt TX, basically like the WaveLAN, have a free space range of about 100 meters. So if you have 2 WaveLAN cards, basically you could hit this entire room with one access point. Of course, it wouldn't work very well from the perspective of the users, but as far as coverage goes, they work at approximately that difference. The antennas on wireless cards are actually pretty poor. In most cases, they're about -2 dB gain. But one of the observations you can make about that is they only perform incrementally more poorly in the vertical space as they do in the horizontal space. And that's something you can use to your advantage. For NANOG 26, which is the first of these events that we did last year, we deployed 13 access points, 7 in the main room by itself. So in a relatively small hotel, far smaller than this one, we had 13 access points. We used a mix of 2 antenna types in order to get the density in the one room, and I have a good picture of that here in a moment. But half the antennas are horizontally polarized, and what that did is the antennas on the access points, which in this case are dipoles, are far less sensitive to each other in the horizontal and or vertical plane than the antennas on the wireless cards. So even in places where we have a map coloring problem and things are on adjacent channels, the likelihood of the access points interfering with each other is significantly lower in this case. We were also able to reduce the output power on the access points themselves, which has the property that the wireless cards and the clients will associate with the access point they see with the strongest signal. If you have 6 access points in a room like this, all transmitting at 30 milliwatts, it's going to see at least 3 or 4 of them at approximately the same signal strength, and so it will probably stay associated with it with the one access point, regardless of where you move in the room. If you can reduce the power to the point where not all the users will end up associated with the same access point, say the one by the door where everybody powered up their laptops or came into the room, then you're in a situation where the load can actually be distributed reasonably across all the access points. So there's a horizontal access point. It's very high tech. It's rotated 90 degrees from being a vertical access point. The practical result of that, actually, if you look at it, is it has the same radiative pattern as a dipole would ordinarily have. It's just that the donut goes forward and back instead of all the way around the thing. So in this case, in lieu of using an external antenna, we can use the internal antennas in the access point, and we get patterns that look like that. So all the horizontally polarized access points basically have a footprint that is rectangular, and they're far less sensitive on the edges than the vertically polarized access points, which have a traditional dipole pattern. IETF design, much bigger problem. Instead of 550 people, we planned for 2,000 people. In Yokohama, we saw more than 1,400 people in one room associated with the wireless access points. So the IETF problem is much larger, and you could apply it to other large venues like sporting events, where potentially you could deploy wireless access for order of 10,000 people using a similar method. Gets us into the address space problem. The address space for that wireless subnet was a /20. The total address space that we had was a /19. Not all of those users were on at the same time, but we handed out about 3/4 of that address space, which is a big number. It's hard to do things like crank your DHCP lease time down and have any kind of reasonable persistence. So you really need the amount of IP address space that you need in order to do this. And in this case, the lease time is set around 8 hours, which would get somebody associated with the thing for basically the whole day, even if their machine got turned off. Again, reduce the output power to 15 milliwatts. Not all of our equipment was Cisco in this case. So the gear stuff, which has a fixed radio output of 30 milliwatts, we used a density setting of high, and I'll explain what that actually does here in a moment, where possible. So the IETF 55 layout is a much worse map coloring problem. Given only 3 channels and one rogue Japanese access point, which is down in the corner there, you don't have a whole lot of choices. But you can see there's 27 access points on the one floor with all of the users, and in fact, during an especially boring IPv6 meeting, there were more than 700 people on the wireless in one working group. During the plenary, it actually peaked at around 1,100, which was significantly smaller than Yokohama, but there were fewer people there as well. Logical layout for that network ends up looking something like this. We have a couple of small backbone switches, and the interesting problem with this hotel was that there were a number of Ethernet runs that were in the range of 150 meters, which is, significantly out of spec. But that actually worked pretty well. Some complaints about enterprise access points that we've experienced in the process of attempting to deploy this. Some access points allow you to set output power. That would be like the Cisco's, and some use density or sensitivity settings, and that would be most of the OEM Avaya equipment that's available from all sorts of vendors. And what density settings do is, on the access point, they limit the quality of the connection that the access point is willing to tolerate from a user. So the access point will disconnect a client that reaches a certain threshold. And what happens is, in situations where you have marginal antennas or marginal quality and all of your access points are marginal from the perspective of a client, the client will associate with an access point and then get disconnected. And whereas if you have the opportunity to use power settings, the access point or the client simply won't hear the access points in the same situation. So clients tend to flip-flop on because in many cases they can hear the access point just fine, but the access point can't hear them. One vendor provided us with access points for which it was impossible to determine how many stations were actually associated with the access point. And that was kind of interesting because we know that the access points get in trouble when they have a really large number of users on them. And in this case, this access point would send an SNMP trap when it crashed that said that the MAC table on the card had filled up. So we knew that the access points had too many users associated with them. We just didn't know how many immediately beforehand, so there was nothing we could do about it. So it had an Ethernet bridge MIB that wouldn't age, which is sort of an interesting idea. It's like how many people are actually on this thing. And it had no enterprise MIB from which you could tell what associated stations were. IAPP, which is the Inter Access Point Protocol, which has been in IEEE standardization process since 1997, is not, in fact, standardized between vendor platforms at this point. So, for example, Cisco's can see IAPP messages from Avaya access points, but not the other way around, which has the interesting property that some of your access points can tell how many users are on some of your other access points, but not vice versa. Crashes tend to lead to cascading failures, so when you don't know how many people were associated with it, when that access point blows up, all those users move over to the next available access point in the same space. So that access point then blows up because it becomes overloaded. So you can watch the crash go around the room, and in fact you can watch the frustration level among the users go around the room as well. One vendor's access points would give up attempting to DHCP after 4 attempts, and then they would, one, assign themselves a RFC 1918 address, and two, lose random bits of their configuration. So by the time you found the access point, let's say you powered it on without plugging in the Ethernet and it was unable to DHCP, by the time you found that access point, it would be in some unusable state. So if you were having network connectivity problems with various portions of your network, your access points might go into a hosed state and never come back. Interoperability issues with some older cards, and this, when you have people who have a broad variety of hardware, and you know, we now have 802.11 cards and old intersil prisms and other things that are now more than 4 years old, and they don't support all of the features of 802.11b. So things like short preambles at very low bit rates they don't support. So you have to do some tweaking to your hardware in order to actually get all varieties of cards to working. Now there's some question as to how obsolete you want to choose to support, but when you have users complaining and you know why, it's pretty hard to not justify tweaking it. You need real management tools for all access points. At this point, they'll provide you with, in most cases, an SNMP management interface, which is SNMP v1. They will provide you with a web-based management interface. They may provide you with a CLI, which will be via Telnet. And in all of these cases, you have to pass the management password in clear text. So, I mean, an SSH or SSL wrappered management interface would be really nice. I mean, we have those on switches now. It can't be that hard to implement on an access point. One access point model would actually provide management passwords to anyone who asked by sending a magic broadcast packet to the network. That was kind of cute. And as far as client issues, in terms of tuning the network, not all wireless cards are created equal. By the standards of wireless cards, the OEM Avaya and Lucent Technologies cards are actually pretty good. When you get into the ones that are built into laptops, particularly laptops that are made of metal, the actual performance of the wireless cards is quite poor. When they say that the distance they recommend on the Apple G4 Titanium laptop, the original one is 100 feet, they aren't kidding. So what happens is when you use those in places where you have sensitivity settings, some of your clients may work while others don't, simply because their antenna is too poor. And so at that point, the only real solutions are increase the number of access points, which you may have trouble doing because of your map coloring problem, or cranking the sensitivity setting down, which has its own issues, because one of the things you're using the sensitivity setting to do is allow you to set the broadcast and multicast rate higher to say 2 megabits or 5 megabits, so that you can actually support the amount of broadcast or multicast traffic that you have on the network. So you have trouble supporting marginal clients in extremely high density situations. Misconfigured clients, things that are in ad hoc mode, have which, you know, clearly if they're in ad hoc mode, they're not associated with any of the base stations in your network, so they're non-working. Well, clients that are configured by default will probably associate with the ad hoc network just as easily as they do with the other network. So you can suck half the people in the room down into the non-working pit of despair because of one ad hoc user. And then, of course, those users remain in ad hoc mode and wander around and cause more users to go into ad hoc mode. So, I mean, that can become a support nightmare. And part of the problem there is simply that host implementations of 802.11b controls for various drivers are either lacking or hiding critical control functionality from the user. And Microsoft is certainly an offender there, although the Apple stack has its own problems, which have mostly been rectified by now. What does the future hold? The map coloring problem will get a lot easier with 802.11a. You have somewhere between 8 and 10 non-overlapping channels depending on the equipment you're using. Those are available at various powers, up to 800 milliwatts, I believe, is the acceptable maximum. That's a orthogonal frequency division multiplexing scheme as opposed to the CCK one that 802.11 uses. And as a result, it ought to be slightly more resistant to interference. The problem with it, though, is that the power requirements of the chipsets that are operating in the 5 gigahertz range and the size of the antennas that are required to perform decently is probably going to keep those out of any devices smaller than laptops for the foreseeable future, which means that 802.11b is probably going to be around for quite a while. 802.11a and b access points are kind of a no-brainer. All of the enterprise vendors are pushing products that do both. Some of them have better implementations than others. The range on 802.11a is going to be significantly more restricted on any device that doesn't have a largish external antenna. So the density you're going to need to support that is even larger. 802.11g, same rate, but we have the same 3 channels we have now. One of the issues that's being hashed out by vendors is that if you transmit at what would be considered full power, like 100 milliwatts or so, on channels 1 or 11 with an ordinary antenna, you're actually going to leak outside of the 2.4 gigahertz ISM band into the adjacent bands at kind of unacceptable levels as far as the FCC is concerned. So you may end up having only 2 non-overlapping channels if you use, say, 3 and 9, or you might have to significantly reduce the power you use on 1 or 11. In any event, you're sharing that spectrum with all the 802.11b devices. Your access points may be backward compatible, but I think ultimately what that's going to do is sort of hinder the adoption of B and G dual stack devices. People may end up just paying for the chipset and using it one way or the other. Performance may not be significantly better than one expects now, except in your home environment where the nearest access point might be several hundred meters away. On laptops, we basically solved the problem of power consumption on laptops as far as wireless chipsets go. I mean, when you have a monster like this that has 120 watt hours of batteries, the actual impact of a wireless card on the thing is negligible. On PDAs and cell phones and other devices, we're probably going to stick with B and G until the power and size requirements for A go down. And given the need for high-performance antennas there, the size requirements may never go down to some level that's acceptable for things like PDAs and cell phones. I'd like to thank all the people that helped me with this, Merritt and the University of Oregon and Nokia and the IETF Secretariat for allowing me to mess up their networks. Bill Fenner and Carlos Vincente, who did the tool development for the monitoring stuff that we used at NANOG and IETF, David Cousins from Nokia, who bought all the access points, Jennifer Adams from Cisco, who actually provided a large number of access points, and everyone who worked on NANOG 26 and IETF networks. Thanks.
Thanks, Joel. Do we have time to take some questions? If you can, direct it to the speaker who you'd like to have answer it.
Just a quick comment from the guys from Tennessee on finding rogue access points. I posted to the list. It hasn't made it there yet. I don't know if it's just the list is slow or if I fat-fingered something. But there's some other ways that you can track APs. One cool trick we found is a few APs actually do multicast. So on your edge interfaces, you could look at the IGMP groups and see what access points are doing multicast that way.
You do. So you will check that on your Ethernet?
You can check it on all your interfaces where you have multicast. You can just do a show IGMP groups on your routers.
Have a database of all yours and then compare that to.
I posted something to the list, so as soon as it shows up there, you take a look at it. And appreciate any feedback if anyone has any additional groups or information that I missed.
Actually, yes, hello. Okay. Joel, are the tools and stuff that you guys or that the U of O folks, Fenner et al. Developed, are those going to be made available out through the community?
I think we'd like to. They're not packaged in any sensible format right now, but the person to ask on that would probably be Bill, since he has most of the effort that went into doing those. They are actually quite cool for something that's you know, a relatively minimal scripted interface. They actually work a lot better than the enterprise tools that we've paid a lot of money for.
Isn't that usually the case?
Yeah, so a lot of the scripts were just things that I came up with on the fly to solve a given problem or something, so they're not like nice polished things. But yeah, I mean, I don't see a problem with making them available. I might keep the one that steals the password from the base station. But other than that, yeah.
Disclosure. Well, yeah, I mean, in the interest of full disclosure, we've given that vendor a fair amount of time, so I think it's time to revisit with them whether or not they've actually solved that.
And if I can, since there's nobody else, I have one other question for the University of Tennessee folks. Have you found issues with people other than your frat and sorority groups pushing Yaggies towards you? Have you found any widespread bad things happening with people using the network in its sort of open mode? I guess my question is coming from the sense that I get Homeland Security and folks like that are out saying we need to really lock down our wireless networks because they could cause evildoers to do bad things and stuff like that. So have you noticed, or do you have any preparation or any ability to notice bad things happening on that network?
No, we haven't noticed anything so far, and if the Homeland Security people want to come and help me, they're welcome. But that will be their duty, I guess. No, I mean, it's really about convenience. So I would love to secure that thing, but please, with convenience, because then you lose everything that you did, yes? So I think if people just learn how to protect themselves, it would be a lot better.
Well, this is primarily for Joel. Every year I work a show that does very large, wide area coverage with wireless, 802.11b. This year, the people from NCSA who set up that network ran everything on a single channel, and we had extremely good results. I'm not an RF person by any means. My last RF class was mumble years ago, so I don't claim any expertise, but I was wondering if you'd ever looked at such a solution where you covered large areas with large numbers of access points all operating on a single channel.
Well, I've had relatively negative experiences doing that in small areas. One of the vendors suggested solutions to the crashing access point problem was simply to put two cards in the access point on the same channel. But what happens at that point is you have the same collision domain, and all these things are operating in IBSS mode. So the access point assumes that it actually has control of who transmits on that channel to some extent, and as a result, you have, I think, more issues with people stomping on each other than you would otherwise have. I mean, a large portion of it has to do with the size of the packets you were sending and how many people were sending them at once. Because I could see situations where you have large amounts of relatively small packets, UDP for example, that you could push out in one direction or the other on the same channel and not smash each other. Whereas when you have extremely large packets, on the other hand, I mean, right up around 1,500, the probability of one of them getting smashed and having more queuing as a result is much higher. But a lot of whether or not it performs acceptably has to do with the utilization on each access point. And in the IETF situation, you see things where the access points get very close to 4 megabits. And at that point, everybody starts to suffer. And if there's more noise on the same channel, then people start to suffer more than they would otherwise.
Thank you.
One second. Let's take these last two questions, and we'll take the other ones offline. One other request. Can the AV people give us a clue about how to bring up the mics on the tables up here?
They'll come up when you just start talking into them.
Really?
Yeah.
Okay, we had no success with that.
Eric, we need the portable mic.
You have the lab. Yeah.
Hi there. I had a question for Joel. Have you given any thought to what happens if you roll into a venue where there is already a wireless network deployed?
When we did the site survey for the hotel in Atlanta, we discovered, I mean, it's basically surrounded by 40-story high buildings. So, I mean, in the process of doing the site survey, we discovered about 15 wireless networks that you could actually hear. In hotels, it actually turns out not to be much a problem because these buildings are so large and they use so much concrete that the actual amount of interference is small. At the point where people start deploying wireless networks that cover hotels, it's going to get more interesting. When you look at something like the STSN network deployments that people are doing in hotels, they're not providing nearly enough address space or network infrastructure that an event like the IETF could just pay whatever it costs to use their services for the course of the event. So I think in many cases it's going to end up being a negotiation between whatever wireless ISP is already deployed there and the whatever network you have to deploy in order to actually get reasonable service. Because, I mean, if you look at it, the remaining address space available in V4 would amount to about 200,000/19s, which might cover every venue that you could conceivably like deploy that kind of wireless in, but it wouldn't leave much left over for anything else. So it doesn't look to me like venues are going to come up with things like large amounts of address space and wireless networks in order just to support flash crowds. So I think the biggest issue is negotiating with whoever's there first.
Yeah, thank you. I was thinking more of an interference issue rather than anticipating that they'd be able to handle this amount of traffic.
Yeah, I mean, that goes along with it. As long as there's relatively few people. I mean, if the existing network is there for the convenience of the hotel staff, then it's going to have relatively low traffic on it, and it's mostly just then an issue of ensuring that you don't stomp all over it completely. That's about all I can think of in that environment.
Okay, hey.
Louis, you're going to hate me. You're going to hate me. We're going to have to take your question offline. I'm sorry. So thank you, Joel and Philippe.